Hi, I'm Bob Alexander. I'd like to show you this test instrument I made. I call it a logic meter. It does some of the things a logic analyzer might do, but it's more convenient, faster to set up, and easier to use. I'm going to demonstrate the features. I'll open it up and talk about the design. I have posted the schematic, board layout, and source code online. You can see the link below in the YouTube description. It is my hope that someone will take this design, or at least this idea, and turn it into a commercial product. If you do that, please let me know. I would love to be able to buy a professionally made version of this. The most obvious thing about this is its resemblance to a multimeter. It starts with the selector knob, and I think that contributes a lot to its ease of use. There are 5 menu buttons, there's a help button, there's a 0.1 inch header for the test leads. I've labeled it P for primary, ground, auxiliary A, and auxiliary B. There's a USB port on the side for charging the built-in LiPo battery and communicating with the PC. Going around the functions, we have servo, pulse width modulation, UART in, UART out, SPI in. There is no SPI out yet. That's a future enhancement. GPS simulator, a mini logic analyzer, to be determined, and various utility functions. Let's start with the servo feature. So, what does this do, and how do I wire it up? Well, I can find out by pressing the help button. And it says it outputs a 50 Hz signal compatible with most servos with adjustable pulse width. And for wiring it up, it says that the primary pin is the servo out, auxiliary A and auxiliary B are unused. Press done. Now, it's a little embarrassing to admit this, but I do not have a spare servo lying around. So I'm just hooking this up to my oscilloscope, and you can see that indeed there is a 50 Hz signal with a 1.5 millisecond pulse. We can change the width of the pulse by pressing the pulse button, and it shows 0.0015 seconds or 1.5 milliseconds, and I can adjust that up or down. I can move the cursor to another digit and do a more fine adjust. Now there's 2 feature enhancements that this brings to mind. The first is that the signal the logic meter is sending out is a 3.3 volt signal. That's because all the electronics inside are running at 3.3 volts. There are some microcontrollers that allow a set of pins to be powered at a different level. So you could add the feature that the output voltages are adjustable for both servo and all the other features. The other idea I had was, if I did have a servo or some system under test, I would have to perhaps drag out my power supply, power the servo from the power supply, connect the power supply's ground to here and to the servo, and then I'd be able to demonstrate this. But what if the logic meter could act as a power source for small systems under test, systems that don't require a lot of power? So for example, we could put banana plugs here, power and ground, and maybe have a slide switch to control whether it's outputting 3.3 volts or 5 volts, or get even fancier with the user interface that lets you adjust the output voltage coming out the banana plugs. And that way you'd be able to power a system under test right from the logic meter more conveniently. Alright, move on to the next function, pulse width modulation. This is very similar to the servo, though here you can control both the width of the pulse and the frequency. And if you want to think in terms of hertz, you can press the frequency button and change the frequency that way. If you want to think in terms of seconds, you can change it by pressing the period button. Likewise, you can change the duty cycle as a percentage or a pulse width in seconds. So for example, if I change the frequency, right now it's at 2 kilohertz. I can move the cursor left and change the frequency to something lower, all the way down to 0. Alternatively, I could change the period. Right now it's at 3.3 milliseconds. I could change that. Duty cycle lets you change the percentage. Pulse lets you change the seconds of the pulse. And now I have another idea for a new feature. Right now this is sending out a steady pulse width modulated signal. What if you wanted to manually trigger a single pulse? We could add a button changing the mode from continuous to single, and then have a button that triggers an individual pulse. Or hold the button down and you get a train of pulses. Let's go to UART in next and go to another bench to play with that. So this is a mailbox alarm that I made. There's a microcontroller out in my mailbox at the curb, and it sends a signal here when the mailman leaves mail and raises the flag on the toy mailbox. I can output debugging messages over the UART from the microcontroller here. This is actually what originally motivated the logic meter. Being able to have a mobile device that I could quickly and easily hook up to a microcontroller and get debugging output. So how do I wire this up? Well, let's press help. Displays incoming UART data. Primary pin is UART in. A and B are unused. I already knew that, so it's already wired up. I can set the baud rate to any number of standard values. I can also set it to auto baud, which is the default, and it will look for rising and falling edges and calculate the baud rate. So let's do that. And now, through the magic of video editing, I will go outside and trigger my mailbox and be back in less than a second. I'm back. Did you miss me? So we got all the debugging output from the microcontroller, and we have some scroll buttons. We can go up or down and review the data. And once we're the baud rate has been detected at 115,473 bits per second. And we can clear the screen if we want. I've moved over to my computer to demonstrate another feature of the UART in. You've seen it display ASCII characters, but what if some non-ASCII characters come in? So I've hooked up a virtual COM port on my computer, a USB virtual COM port, to the input of the logic meter, and I'm just going to type a few letters, HELLO, to show that it's working. And now if I type some control characters like Control A, Control B, Control C, and so on, you see they're displayed as hexadecimal inverse video digits. So UART in currently supports one input. A good feature enhancement would be to add a second input, and that way you could monitor both sides of a UART conversation that a microcontroller is having with another microcontroller or with a device. Moving right along to UART out. I'm still at the computer. I can press help, and I see this outputs UART data. The primary pin is unused. Pin A is where the UART data is going to go out, and I've already wired that up. Pin B is unused. And what this allows me to do is send UART data out to a device. I'm going to just send it to my PC. I've got a terminal window opened up, TeraTerm, on the USB virtual COM port. And on the display it says ASCII characters. That is a description of what data we're going to be sending. And the current status of the sending is stopped and looping. Looping means that we send the data over and over again. Stopped means we're not currently sending it. We can change the baud rate. I've already got it set to 9600 baud, and that's just fine. And if I want to send one set of ASCII characters, I can press start, and it sent it to the PC. If I wanted to continually send characters, I could press loop, and it repeatedly does it, and I can stop that. Now, just being able to send ASCII characters is useful for testing that UART communication works, but you might want to send more specific data. So we can copy a file from the PC to the logic meter and then use that as a source of data instead. To do that, I'm going to switch to the utility function and plug in a USB cable. We have a logic meter drive, and I'm just going to copy a file over. Zero-G toilet. It's the instructions from the movie 2001 on how to use a zero-gravity toilet. And we switch back to UART out. And now we press the data button. And we have two choices now. We can send ASCII characters or we can send zero-G toilet. So I select zero-G toilet. And now it's saying zero-G toilet there, and when I start, it sends the instructions. I'm going to pause that. Let's look very briefly at SPI in. We can press help again. The primary pin is SPI in. The aux A is the SPI clocked, aux B is the SPI select, like chip select. And this displays incoming SPI data. So it's much like the UART in, so I'm not going to demonstrate it, but I wanted to point out one of the nice things about this. At the top, it says what the current polarity and phase setting is. We can press setup mode. You can change from polarity 0, polarity 1, phase 0, phase 1. One of the difficult things to get right in SPI is getting those parameters right. So you could have this hooked up to an SPI device that's sending out data and just come here and play with these buttons until you start getting the data you expect appearing on the screen. That can help you debug certain communication problems with your microcontroller. One other thing, you saw UART data was being displayed in ASCII. That's because UART data frequently is text. It's very rare for SPI data to be text, and so this always displays hexadecimal characters, just like when the UART in was getting control characters. Next feature, GPS sim. This is really cool, I think. It outputs simulated NMEA sentences. The primary pin is unused, pin A is the UART data being output, and pin B is unused. And it's a map, of course, and you can change the latitude. You can change the longitude. You can change the time and date. So if you have any device that relies on GPS data, you can use this to simulate any time or place. You can test how your code handles daylight savings time or locations in different countries. Before we look at the logic analyzer, I want to talk a bit about utility. You saw me use it before. When the logic meter is in utility mode, you can connect it to a PC and it appears on the PC as both a USB drive and a virtual COM port. So you can copy files to and from the logic meter, but you can also use it for remote control. None of this has been implemented yet, but if you're familiar with the Bus Pirate from Dangerous Prototypes, it's a small USB device that has a command line that lets you control a set of pins. It implements UART protocol, SPI protocol, a few other things. I could imagine functionality like that being built into the logic meter. There could also be configuration options here, screen brightness, screen timeout. Alright, let's go to the logic analyzer. This is a low-end logic analyzer, and it's still a work in progress, but I'll show you what I have. It's still hooked up to my computer to a serial COM port, so we're looking at UART data. If I hold down a key, you can see it's getting some data there. It supports up to 3 channels. You can press the channel button, turn on channel 2, channel 3. I don't have anything hooked up to channels 2 and 3 right now. The mode, auto, normal, single. The rate, 10 kilohertz, 100 kilohertz, 1 megahertz, 10 megahertz. Trigger, you can select the channel and it goes from one to the other. You can select the edge, whether you trigger on the falling edge, either edge, or rising edge. And the position, that I haven't implemented yet. So we're now in trigger mode. Before we were not. Now we are. I'm going to press a key on the keyboard briefly, long enough to send 3 characters, and you see it's been triggered. The current trigger point by default is in the middle of the screen, and we captured 3 characters. There still needs to be a way to zoom in and out on that, change the time base, but what I can do is over on the computer, I'm going to change the baud rate. I can't change the time base, so I'm changing the baud rate. So now at a baud rate of 600, we start to see the individual bits in the character I typed. Let's take a look inside, shall we? Okay, we have a LiPo battery super glued in place. We have a PIC32 MZ with 2 megabytes of flash and 512K of RAM, running at 200 megahertz, a speaker. There's some battery charging circuitry under here, and that's it. Here's the test leads. The test leads go to 5 volt tolerant pins on the PIC. Each test lead goes to 4 different pins. The PIC does have peripheral pin select, so you can wire different pins to different peripherals, but they are in groups of 4. And so by wiring 4 pins to each test lead, I give myself maximum flexibility. I'm not using all that flexibility, but it's there. I'm using an off-the-shelf rotary knob for the selector switch. If you were making a professional version of this, you'd probably want to use a multimeter style lead pattern on the PCB. I'm using an LCD that I bought off Amazon on a module. If you were making a professional version of this, you would not use a module, you'd use a bare LCD. I'm interfacing to it through SPI. You could get some more speed by doing a parallel interface, but I think it's been fast enough just with SPI. I update the display using DMA, so the microcontroller is able to continue processing while the display is being updated, and it works fast enough. And this is it. You know, I've posted the schematic online, but if you have an engineering team, you might as well start from scratch. This is so dead simple. And there are some things you'd want to change anyway, like the rotary switch and the LCD. Any company that has experience with multimeters or handheld oscilloscopes would be able to whip something like this out in no time. Most of what the logic meter is doing is pretty easy and obvious. It's using UART peripherals, SPI peripherals, pulse width modulation peripherals, but the logic analyzer feature is more complicated, so I thought I'd explain it here. We have the 3 test leads coming in, primary, aux A, and aux B, and they're coming into the PIC32's port D on bits 0, 1, and 4. So we can sample all 3 signals by reading a single byte. We set up DMA channel 1 to read that byte and copy it into a 64K buffer. DMA1 is triggered by a timer, in this case timer 4, and we control the sample rate by setting the frequency of timer 4. Every time timer 4 rolls over, the DMA will sample the current values in port D and copy it into the buffer. One thing to be aware of is that DMA is using the same data bus as the CPU. So if the DMA and the CPU are both trying to access the bus at the same time, one of them will have to wait, and sometimes it will be the DMA. That will introduce some jitter into the sampling. The CPU runs at 200 megahertz. I've set the maximum frequency sampling rate to 10 megahertz in the software. So I don't know if the jitter is going to be a problem at that speed, but it's something that has to be tested. Once the buffer is filled up, DMA1 stops, and the PIC32 has a feature where 2 DMA channels can be chained together. So DMA1 is chained to DMA2. It will automatically start DMA2 when it is done. And DMA2 will continue sampling the inputs and copying them into a second buffer. And DMA2 is also driven by timer 4. So now we have a 128K sample buffer, but we can do better. While DMA2 is running, the software can come in and modify DMA1 so that instead of copying to that buffer, it copies to that buffer. And then DMA1 can be chained from DMA2. So when DMA2 is done, it starts DMA1. This is called ping pong DMA. DMA1 runs. When it finishes, it starts DMA2. When DMA2 finishes, it starts DMA1. And meanwhile, the software is changing the pointers to the buffers that the DMA writes into. And so we build a circular buffer there of 192K. So the PIC32 has a total of 512K. 170K of that is being used for the display buffer. 192K is being used here. Some of it needs to be used for the applications, but it would be possible, perhaps, to add another 64K buffer here and have a total of 256K samples. That's still pretty small for a logic analyzer, but as I said, this is a low-end logic analyzer. The next question is, how do I handle the triggering? The PIC32 has a peripheral called input capture. It can monitor the status of a pin and trigger an interrupt based on a rising edge, falling edge, or either edge. So let's say we want to trigger on a rising edge of the primary pin, we configure the input capture to monitor the status of that pin, and when the rising edge happens, it triggers an interrupt that starts DMA3. DMA3 is configured to copy a value from a memory location, in this case hex 8000, into timer 8's control register, and that has the effect of turning timer 8 on. Timer 8 is set to the amount of time we should continue to collect samples after the trigger. When timer 8 expires, it triggers DMA4, which is configured to copy the value 0 into timer 4's control register, which has the effect of turning timer 4 off. With timer 4 off, the DMA channel stops sampling. The software can come in, see which DMA channel was currently active, figure out where it was last writing in the buffer. The sample after that, in the circular buffer, is the oldest sample we have. So we just start there, read the rest of the samples, and draw the traces. So there you have it, the multimeter. I built this as a hobby project. I've thought about starting a company and trying to sell them, but I don't want the work. So I commend this to the internet. If anyone out there wants to take this idea, it's all yours. All I ask is that you let me know so I can buy one from you. I hope you enjoyed this video. Thanks for watching.